Welcome to the Cosmic Pie Podcast, episode 38, season 3. I'm your host, Wayne Barkhouse.
And I'm Robert Moore.
We are broadcasting live on the campus of the University of North Dakota here in beautiful,
And starting to be snowy.
hardly snow, just a little bit of snow. A lot more people have more than we got, we'll put it that way.
Oh, yeah. Cleveland got a little bit more. And
We've had, what, about an inch of snow maybe altogether?
maybe.
Somewhere around there. Anyways, we're broadcasting live, as I mentioned, from the campus of the University of North Dakota. As a disclaimer, Robert?
Well, the opinions expressed herein are those of myself and Wayne, not the university, definitely not the Department of Physics and Astrophysics, or the College of Arts and Sciences. So, just speaking for ourselves.
Just for ourselves. Now, we do have a live chat feature that's running, so if you have any questions or comments you'd like to make throughout the podcast, feel free to do so. And as also a reminder, we do upload our podcast the next day on Spotify. You know why we do it the next day, Robert?
Well, because YouTube has a problem of letting you download the videos until a day later.
Yeah, it's not until the next morning, tomorrow morning, that I'm actually able to grab a hold of the podcast itself and do stuff with it, which is why you don't see like a nice thumbnail put on there and stuff, because I like to capture a frame through the actual podcast itself. Now that you said that, I'm going to catch you in this odd...
Yep. I was about to say, there's the frame. You'll see.
Do it one more time. Give it a few longer. Hold it. Okay. That's how you normally look, isn't it? No, just kidding.
Yeah.
That's when we tell Robert he has to work Saturday. That's the look he gives us.
Oh, Lordy.
Anyway, so we're going to start with Here Comes the
Sun.
Sun. Who sang that?
I would have known if you hadn't asked.
The Beatles.
It is the Beatles.
Yeah,
Yes.
George Harrison sang
George
that.
Harrison. Yeah.
Yeah. Okay, so we're going to start with our favorite star, our own sun. Look at that mess you see there, pointed out by that beautiful green arrow that some creature put there.
I wonder what creature put it there.
The Sunspot Complex. In fact, if you go on spaceweather.com, they have a nice live sort of view of the sun, and you can see the same thing. This is an image taken by the Solar Dynamics Observatory, which is basically the second generation telescope that we have in space that's watching the sun. Mm-hmm. The first really good one was the Soho mission. That's still up there as well.
It is. So and it takes some amazing pictures,
Oh, it
too.
does,
It's
for
just,
sure.
It's in ultraviolet and mild, low X-ray.
Yeah, I mean, it has an occulting disk, so it blocks the sun itself, and we can see like the coronal mass ejections around it.
Right.
But this is a good one, and it's much higher resolution as far as I know of the sun itself, and you can look directly at the sun with the proper filter, of course.
Right.
And what we see is this huge sunspot complex that just rotated into view. In fact, anytime you see things like this, a large grouping of sunspots, they are associated with aurora activity. In fact, I noticed that the alert has gone out for tomorrow evening that we're expecting aurora activity possibly. You never know for sure until it actually happens.
Right.
So it's a little bit unpredictable. Not hugely unpredictable. Anytime you see a solar flare, for example, you can get an idea, if it happens to be pointed in the right direction, that when those charged particles reach us, they can trigger an aurora, northern and southern lights. Not always the case, because sometimes they miss us, or the energy is a little bit less. It also depends on the orientation of the magnetic field of the Earth.
Right.
All of these considerations. In fact, we could have Vincent on sometime in the near future.
Yeah, we ought to have him back.
Have him back, because I'm sure he's got some lovely pictures of the event that happened just the other week as well. And so, yeah, you never quite know if that's going to occur, but the chances go up if you do see this sort of activity.
And big sunspots like that means there's a lot of energy bundled up in the magnetic field of the sun, which is what produces a lot of these effects. So,
yeah, and the other thing is we know the sun, in terms of its activity, is roughly at the solar peak,
right,
solar maximum, and we don't quite know where that peak is. It's only like months and months later, you look back at the activity, like the number of sunspots and so on, and say, okay, this was the peak in July of whatever, right, 2025, let's say.
Right.
So we're not sure if we're past the peak or not, but we'll know probably within the next 12 months or so if that's the case.
So,
Now, the interesting thing about the sunspot complex, if you actually look at the physical size, and this was something that I thought was quite interesting. This is on spaceweather.com, that they have a comparison The Sunspot Complex today, and they're numbered so you can keep track of them. So you see the 4296 and the 4294 relatively close together, and they can interact, right, magnetically.
Absolutely.
So they can really, if you like, increase the superposition type of effect, where they increase their effect on the space weather around the sun, and ultimately including potentially around the Earth itself.
There's that much greater potential for the lines to get tangled up, which then when they break is when you get a flare because of the release of energy involved with that. We get all kinds of reconnection events, so forth.
Yeah, and that stuff has been studied a lot by the Parker Solar Probe.
Okay.
Right, it's gone a lot into furthering our science of these reconnecting events, and how that relates to the heating of the corona, for example.
Right.
Where there's magnetic energy that gets pumped into the outermost atmosphere of our sun, which gets heated up to like millions and millions of degrees.
Yeah.
And when you're talking millions and millions, you don't care if it's Fahrenheit or Celsius or Kelvin.
It's
just
hot.
it's a high number. It's in the millions. That's all that really matters. The rest of it is rounding off errors in some sense, right? And people often wonder, well, how do you know the temperature is that hot way out in the outer atmosphere? Is because things like during a total solar eclipse of the sun, which is when we can see the corona directly with our eyes. So if you remember a couple years ago on April the 8th, we had the last total solar eclipse that went through North America.
Right.
And you were able to see the corona at that time. But if you take that light and you pass it through a spectrometer or a spectrograph, as we call them, that is, you split the light into the different rainbow-like colors, you can see the presence of emission lines. And not only that, but you can see emission lines from atoms that have lost more than a single electron, so multiple electrons. And that requires a certain temperature to produce the spectral features that you see. And we can use that as a thermometer.
Right.
So instead of saying to your graduate student, hey, put on your rocket boots, go to the edge of the sun, put your thermometer out there, let me know what you read, radio it back so I get the information right away or as soon as possible, right? 8 1/3 minutes. Instead of doing that, which obviously, and then the big joke is
you send them at night.
we were on Extra Bulla's podcast, Extra Bulla, the shout out to you last week, and I mentioned as a joke, right, how would you send a space probe to the sun to study it, and you go at night?
Yeah.
Anyways, and by the way, I3I is just a comet. It's not a UFO.
All right.
I got to put that
It's
in
definitely
there.
not a UFO.
If you want to think about conspiracy theorists, look at the Epstein files or figure out who really shot John F. Kennedy.
Yeah.
But anyways, yeah. So we can use the presence of these emission lines in the spectrum of the corona of the sun during a total solar eclipse that allows us to estimate what is the temperature of that rarefied low-density gas.
I always like pointing out to you, you've got to remember that to a physicist and hence an astronomer, temperature is really just a proxy for the average kinetic energy of the particles involved. So there are very few particles in the corona of the sun, but they're moving really fast. And that's the kinetic energy is what we call the energy of motion. So they have a lot of kinetic energy. They're moving really fast.
That's why when you introduce like the Kelvin temperature scale to a student, you can use the analogy based on what you mentioned that temperature is really just a motion, just a measurement of the average motion of an ensemble,
Right.
a group of objects. For example, you could calculate what is the average temperature of a bag of marbles because it's not a single marble in the bag. And if they were moving around, right, they would have, each one has their own kinetic energy. So you get an average of that kinetic energy would give you an estimate of the temperature of those collection of marbles. So you could never say, what's the temperature of a single marble? It wouldn't make sense. You could say, what's the temperature of the surface of the marble? But that involves the molecules and the atoms that make up the structure of the marble itself. But if we think of the marble just as a single object, then it's meaningless because you want the average of many of them.
Right.
Like, what's the temperature of a single electron? That's meaningless. It's like asking what's north of the North Pole, right? It's a meaningless question in that sense. So then and the Kelvin scale comes in the fact that you can say, okay, if the temperature decreases, what happens to that average energy of motion? Well, it also decreases. And you might say, okay, then how low can I go?
Where can I go that all motion stops?
Right. And that temperature is a really cold temperature of minus 273 roughly degrees Celsius, like minus 460 or something Fahrenheit.
Right.
And we call that absolute zero or 0 Kelvin. Now, technically, people would argue, and it's true, that all motion would never cease because of the uncertainty principle in quantum mechanics. It'd be like something jiggling around, moving around all of the time, like young people who can't sit down in school or something, right?
Like middle schoolers.
And
yeah.
you, and you try to stick that object in a smaller and smaller box, and what happens is they move around too much. They get outside of that box, right? They penetrate through the wall of the box. In quantum mechanics, you think of it as barrier penetration type of thing. So even though you try your hardest to isolate that object into a specific, precise location, the uncertainty in its motion goes way up. In other words, it's momentum. So there's sort of a balance. So you can only do so well both in its position and its momentum.
Yep.
That's the uncertainty.
Or time and its
principle.
energy. Or
Yeah.
There are all these pairs of quantities that the better you know one, the less you know the other one.
That's really the heart of quantum mechanics, that and probably entanglement when you think about it. Right? Those two basic principles probably describes most of what we know about quantum mechanics,
Right.
how things operate at the very, very tiny length scales, right? You know, subatomic particles. But it's not like we don't know how it works. Things work, of course. You have a cell phone, right? We have lots of electronic devices that work fine.
That work fine, and they work because we understand these things.
Yeah, we understand them to a great level. In fact, it's my understanding, to use the word again, that there's never been an experiment ever done in quantum mechanics that violates or goes against our understanding of the principles of quantum mechanics.
Right.
There's never been an experiment.
No black swans.
And so that's amazing when you think about it. And in fact, to kind of extend that a little bit, we have understanding of what we call quantum electrodynamics. You think about how photons and electrons interact and those kind of stuff. And there are values of different things that you can measure. And they're measured, and the theory tells you that the number is, some number point, digit after digit after digit. Like, I can't remember, it's like 9 digits or something to the right of the decimal point. And when you go and measure it experimentally, that's exactly what you get. It is the best theory, the most closely made theory that matches, your theoretical understanding to what you actually measure in a laboratory. I don't think we have that close of a number ever, right? In our understanding of QED, as we call it. And it's amazing when you think about it that we human beings can mix stuff up, for lack of a better term.
And
that
yet it still describes exactly what happens.
That it measures something so accurately in reality, in nature. It's a really amazing. Now, of course, it's not just made up. I'm just being silly about it. That's based on fundamental principles of physics and also experiments that have been done in the past, for example. But it just shows you the power of the mind that can put that stuff together.
Yeah.
And in quantum electrodynamics, as an example, that was worked on by a lot of people over many years. It wasn't something that came, you can think of Paul Dirac, Richard Feynman,
It's getting close to
Julian
100 years
Swinger.
now, isn't it?
Yeah, and a lot of people around the world worked on this problem, and it took a lot of smart people to put this together, and experiments, of course. And so we benefit from the work that has been done in the past.
Yep. Now, you mentioned on this slide,
Yeah.
trying to get back to it, you've got on there Carrington 1859.
Yes, right. Good point.
So what
So-
happened in 1859?
Yeah, so way back in 1859, when I was knee-high to a grasshopper and just finishing kindergarten, well,
You aren't
back-
that old.
imagine how much the Social Security I would collect if I was that old.
Right.
It should go up. It should go up as you get older.
Yeah.
The longer you live, the more you should get per month, just because it's a gift to you for living so long.
Right.
So if you manage to reach 100, like, you should get a lot of money because you're not going to live that much longer. Why not?
Why
Right?
not?
I think the government is planning on you not living that long. Right?
I'm pretty sure of
If
it.
you want a conspiracy, there you go. Right?
Yeah. They're betting you're
They'll
not.
poison our drinking water so we can't live long, healthy lives, right? Because they don't want us to, ride on the medical system and drain the Social Security, which is probably drained anyways. But anyways, back on September the 1st of 1859, and we know this occurred because people were living back then. And in fact, you can go to the archives in your favorite town that's been around at that time period. Probably go back if it had, especially if it had like a local newspaper.
Right.
You go back through, what were they put it on? It'd be all digital now, or be microfiche or something.
Microfiche or something.
And you go back and you can look at that and you actually see reports that were published in the newspaper back in that time. So the night of September the 1st, going into the 2nd, and so on, where people all the way down to the equator essentially were seeing huge, spectacular displays of northern lights. And not only that, at that time, the telegraph system had been invented and was in use in the United States. People actually reported that the telegraph poles, so it wouldn't be telephone poles, they're telegraph poles, actually caught on fire.
Right.
Because the line got short-circuited because of the sudden influx of electrons that got excited in those wires because of the electromagnetic waves that were passing through from this event, right? This huge eruption on the surface of the sun.
Because all of those aurora, we like to look at them in optical, in our visual wavelengths, but they're also giving off plenty of radio waves. And essentially a wire strung between poles is essentially an antenna.
Yes, exactly.
And so it's picking up all those radio signals, converting them into electric current through those telegraph wires, and they caught on fire.
You know, as an aside on that, people have shown, I think, and this has been shown to be true, it's not made up, but people had reported that when you own, like, say, land, like acres and acres of land, and you got it fenced off with barbed wire fence, that during strong auroras, you can actually pick up the noise of the aurora
You
from
can
the
actually
barbed wire.
listen to what they sound
Yeah,
like.
and that's actually been shown to be the true. You know, it's almost like you think about like the. I'm going to date myself if I said where I first heard this, but people had metal braces, right? They report they could hear radio stations, right?
Yeah,
the
I've heard that.
AM, of course,
I
right?
think it was Lucille Ball was the first one.
Was
who
it? I heard
talked
this on the
about that.
Partridge Family. I
Okay,
remember.
yeah.
I think they did a whole episode about that.
Yep.
Long time back in the '70s or something, right?
Yep.
So it's funny, anyways. But yeah, so the Carrington event was a really huge, major type of event that occurred, you know, a little over 100 years ago. And we often wondered, where did it come from? And the drawings that remain by Carrington back then show you the Sunspot Complex that eventually erupted and produced a really strong solar flare that's associated with this event. And back in the time, 1859, the technology that existed, so the telegraph, as we mentioned already, but back then, clearly, we didn't have cell phones. We didn't have satellites in Earth orbit, right? We didn't have the internets, as George Bush said, everywhere, and that we rely on a lot. And how do you know you rely on a lot? Go pull the plug to your wireless router in your home if you have kids and see how long it takes for someone to start complaining. That's how much we rely on the internet nowadays to do all kinds of things, stream our favorite TV shows or whatever you're doing, right?
Right.
Now, back then, fortunately, we didn't have a lot of that stuff around, but people wondered if we had the same type of event today, a Carrington-like event, what kind of damage would that do to our industrial society?
And that's why we have SDO and SOHO and these satellites up there, because they can give us a few minutes to a few hours of warning.
Even days, because a lot of the problem comes from the charged particles, like, for example, protons. And they can take, you know, upward 2 to 3 days, depending on their speed, to get to the Earth.
And so what does that give us? It gives us time to shut down the satellites, shut down the grid, and avoid the damage.
Now, SDO is in orbit around the Earth, so that won't help you.
Right.
By the time it gets to SDO, it's essentially here, right?
Fair.
It's
But
simultaneously.
SOHO's at one of Lagrange
But
points.
yes, and there are other spacecraft that are closer to the sun, like Stereo, right, mission. There are other spacecraft that are closer to the sun, so they would feel that event first before it reaches the Earth. And like you said, we need that warning time. It'd be nice to have half a day if we
would
could
be
get
nice.
it, 12 hours, where you can essentially pull the plug on all the satellites in Earth orbit,
Right.
all the ones that don't have built-in redundancy. And then when the event is over with, which may take a couple days if it's a strong event. Look how long the Northern Lights took when they outbroke on Veterans Day on November the 11th. That lasted for 3
days.
nights,
3 nights.
right?
Yeah.
Of course, it got weaker and weaker. But eventually, you know, it subsides, the storm, as we call it. And so then you can reboot the satellites, turn them back on, and hopefully that they start. The other way to do it is just don't do anything at all and see what happens. But then you put at risk, you know, these hundreds of millions of dollars for each satellite on average. And if all those satellites get wiped out and a lot of stuff on the ground gets wiped out, because remember, telegraph poles burst on fire, stuff got short-circuited, so obviously there's a lot of equipment on the ground that can be damaged if the event is strong enough. That's going to cause a lot of changes.
Right.
A lot of, really, really long-term type of problems. It's going to take a while to put the system back together, and we're talking years, not months or weeks.
Well, I heard one time, this has been about 10, 20 years since I heard this, but the idea of the Carrington event came up in a conversation, and we looked up, and at the time there were only those big major substation centers. There were only like 2 or 3 in reserve ready to be put into place in the U.S. at the time. So if more than 2 or 3 went out, it would take, you would essentially have to put those back in on the plants, for the plants that manufacture the parts for them, to rebuild more so that you could then replace them in the other places. It could take estimated up to 30 years to redo the grid.
It reminds me of the EMP that we talk about with the detonation of atomic weapons, nuclear weapons, that pulse then can overload electronic circuitry. And there's a movie, I don't know, it's a cheesy movie, and John Travolta's in it and other people. And it was a Broken Arrow. Do you remember that one?
I do remember that movie.
And in there, that's what they did. They lit off a nuclear bomb that created an EM pulse and shut down the electronics on a helicopter in a crash.
Yeah.
And just before it hit, they turned off their car, right? So trying to save it. And then they could restart it afterwards, the vehicle they were in. I think it was a Hummer or something, whatever it was in the movie. but the idea, the best thing you could do is take all your electronic equipment that you can and shield it somehow inside of a metal box, what we call a Faraday cage.
Yep.
And a Faraday cage, you want to say a little bit about a Faraday cage in case nobody knows, and relate it to like a museums and yeah.
And essentially what the Faraday cage does is it's a conductive surface. It's any gaps in it must be smaller than the wavelength of the radiation that it's blocking. But essentially, since light or radio are just alternating electric and magnetic fields, a conductive surface will block it, will absorb that energy and protect, therefore, anything that's inside the cage. And so that's what a Faraday cage is essentially you're just putting a conductor, preferably a grounded one, in the way between you and the radio source.
Yeah, so in and magnetism, those type of courses, you learn about a conducting sphere that's just a shell and hollow on the inside.
Right.
And you'll learn that if a charged object, let's say a rod or something, has a static charge on it, and it touches the surface, and if you don't ground it, then the charge gets equally distributed around this shell itself. But it doesn't touch anything on the inside,
Right.
so you have to way to isolate it, right?
At the same time, any charged field inside the sphere cannot penetrate outside.
Right.
So that's the one weakness of Faraday caging a lot of stuff is nothing can reach it now, but it can't transmit out either.
Yeah, exactly. And a good example of that, or one way to think about it a little bit, and this was told to me by somebody in our faculty the other day that had done this experiment. I won't mention the name in case they don't want their name on air.
Right.
They took their cell phone, put it inside a microwave oven, closed the door. And what they were testing for is the microwave oven door sealed tightly enough that you would expect. And what they did, they don't turn it on, of course, but you just put your cell phone in the microwave oven, close the door, and then try to call your cell phone. And it won't work. And it didn't work.
Yeah.
Right? So the cage of the construction of the microwave itself acts like a Faraday cage in a sense. And it blocks, in this case, its purpose so microwaves can't get out of the microwave oven.
Right.
That's why it's safe, to look at the door of your microwave oven to see if your soup's exploding or not.
Yeah.
Or it's bubbling up, and you're not worried about microwaves penetrating your eyeballs and frying them, right?
Right.
And then you instantly go blind or something.
And it's not that the microwaves will make you radioactive or anything like that. They're not strong enough to ionize or to break up molecules. All they're doing is making the water molecules flip back and forth with that alternating magnetic field, and they pick up kinetic energy. And what is temperature?
The average
average
motion.
kinetic energy of the motion of the particles.
Yeah,
So-
I mean, the microwaves are actually tuned to the right frequency that they are optimal for exciting water. 'Cause
Exciting water.
most food is, has the water inside of it.
Yeah.
And you can demonstrate this really easily. Take a plastic comb that's completely bone dry, put it on the dish of your microwave oven, close the door, turn it on for, 2 or 3 minutes or whatever, and then reach in and grab the comb, and you'll notice that it's still room temperature. It hasn't heated up at all because the atoms and molecules in the plastic of the comb are not agitated, not excited by the microwaves,
Right.
because they're not water molecules.
Yep.
So they're tuned to be the most efficient by heating up the food. And you want it that way, right? You don't want to waste energy pumping out all of this radiation at various wavelengths or frequencies. So it excites other different types of molecules. You want it to excite the water itself, the
Right.
H2O molecules.
Because that's what most food is made out of.
Yeah,
Kind of like us.
yeah, exactly. So never put a frog in a microwave oven and turn it on. That's
Yeah,
the moral of the story.
Not
Don't ever do that.
not unless you're interested in cleaning up a really big mess.
Yeah, exactly. Now, the next thing that I noticed that was on the news is about our very favorite object, and for anyone who's an astronomer, whether you're an amateur astronomer or a professional astronomer, the Pleiades star cluster. If you're in the north,
Yeah.
the Pleiades star cluster has to be one of near the top of your list of favorite objects to look at, even through a small telescope.
And it's also one of the most mistaken objects because it has a small dipper shape, and because it's fairly tiny, people always go, "Is that the Little Dipper?" Okay, let me clear the air there. The Little Dipper is one in the northern sky where the Pleiades will never be. Okay, and number two, the Little Dipper is only little in comparison to the Big Dipper. So, you're not looking, when you're looking for the Little Dipper, you're not looking for a tiny little object that covers, the Pleiades visual is about what, half a degree?
Yeah.
Maybe?
I mean, the Little Dipper, that's the name I give to my son because I'm the Big Dipper and he's
Because
the
you're
little.
the big.
No, you're exactly right. In fact, the Pleiades or the Seven Sisters.
Yeah.
I mean, there's been lots of names that people have used over the years to describe it. It's something that you can easily see with your eyes if you have normal eyesight.
Yep.
You just have to look at the right time of the year, which is kind of it's in the constellation Taurus, so it's a fall type of observation you see at night.
It's about 30, 40 degrees above the horizon in the east at sunset right now.
Yeah, so very easy to see. If you're south of the equator in southern hemisphere, you're not
You're
going
not going to see it.
You're not going to see it, unfortunately. But you have other things you can look at that
Yeah.
we don't have, like the large and small
small
Magellanic
Magellanic
Clouds
Clouds.
and the Southern Cross and Alpha
Harumph.
Centauri in the center of the Milky Way. I got to stop.
Yeah.
I'm going to run out of time here. So they're okay, right? But anyways, so their new paper has recently come out. So this was back last month in November about people using data from both the TESS spacecraft.
Okay.
So that's the spacecraft that we use for looking for exoplanets around other stars. And Gaia, which is the spacecraft that just wrapped up back in January, so almost a year ago, obtaining data. And its primary mission was to use stellar parallax to measure the distances to as many stars as it could, and also get an idea of their actual motion through space as they orbit the Milky Way galaxy, what we call their proper motion.
Right.
Now, relying on those data sets, what did they, first of all, the distance to this object, we should go on and talk about the nature in case you don't know. This is one of these objects that we call an open star cluster.
Right.
So an open star cluster, sort of a typical type of properties. It's fairly young in comparison to like the age of the universe, typically somewhere, hundreds of millions of years old or so. And because it's young, if you assume that the stars in this cluster formed at approximately the same time, which is not bad of an assumption, it's not exactly accurate, but it's not bad, then that means that what happens is you're forming massive stars and low mass stars and everything in between. And because the life expectancy of a star is directly related to its mass, and the relationship is such that the higher the mass of the star, the shorter its lifetime, not the longer, the shorter, because it needs to burn through its fuel much more rapidly to maintain support against gravity trying to collapse the object.
Right.
And therefore to burn through your fuel very quickly, like a car that's very inefficient in terms of the mileage it gets. It can run out of the gas before a nice little small car, even though it has a smaller gas tank, but it's burning through its fuel much more efficiently
Much
and
slower, yeah.
can go a longer distance than the larger car with the larger gas tank. So massive stars have shorter lives than low mass stars. And when you actually look at the different types of stars you find in an open cluster, most of them have, fairly decent sized masses. So we know it's fairly young.
Right.
If it was really old, then all those stars would have long since evolved away.
Right. They would be giants and supergiants and so forth, like dying stars.
And in contrast to these type of star clusters, these open clusters, we have the globular clusters.
Mm-hmm.
And those are different in the sense they typically contain up to even 1 million stars.
Mm-hmm.
And also they're very old stellar populations. So you don't find the very massive stars, what in astronomy we would call O and B type stars. They've long since evolved away, went supernova, and are now like neutron stars or black holes. They're end states.
And another difference that I like pointing out is globular clusters are usually on the halo, the outskirts of the galaxy, whereas open clusters tend to be down in the galaxy, in the disk.
Yeah, and in the spiral arms associated with it. Yeah, the globulars, you'll find them occasionally near and in the disk area, but that's because they're moving through that region at this given moment. But if you trace their trajectory, their path, they actually came from the halo.
Right.
And they'll pass through the disk out the other side and
back
back
out
into the halo again, just in the other direction, obviously. Yep. So this particular open star cluster, it's only, quote unquote, in astronomy, it's only 444 light years away, which makes it relatively nearby. That's why you can see it with your eyes. You don't need binoculars or telescope to pick it out. It has an extent and a size associated with it. But this latest study is showing us something very interesting. But before we get to that point, and Robert, I know you want to make the point. I'm going to let you make the point. But before we get there, the other interesting thing about this particular cluster, and there you see a nice, beautiful, classical view of the Pleiades cluster.
Wish I had an image I'd taken that was half that good.
Now, with a telescope, you can see the stars, and they're obvious to you, the concentration of stars in this image. But the other stuff you see is the blue light all around.
Mm-hmm.
And that blue light, you want to mention what that is?
It's a cloud of gas and dust that the cluster is moving through.
You're spoiling it.
Oh, sorry. But yeah, it's called a reflection nebula.
Right.
It is not being heated. It is simply reflecting the light from those bright stars.
Yeah, notice the light is blue light.
Mm-hmm.
The interstellar dust preferentially scatters in the optical blue light than it does the longer wavelength light.
Right.
It's analogous to the type of scattering that occurs in our atmosphere during a nice clear day. You see the blue sky, and you might ask as a child, why is the sky blue? Why isn't it green? I want the answer now. You're a grown up. Give me the answer. And then you say to your child, yeah, you'll learn that in school. I don't want to spoil it for you, right? So,
or you're like me and you start getting into
Rayleigh
your
scattering.
Rayleigh scattering and all that.
So
Bond lengths.
The answer is that the particles that make up our atmosphere, the gas, the molecules, and the atoms, are of a certain size. And the size is such that the blue light from the sun is more scattered than the longer wavelength light. So if you actually measured the amount of blue light coming from the sun, if you're on the ground making your measurement, it's actually less blue than if you made that same measurement above our atmosphere. Because not all the blue photons coming from the sun heading towards you gets to your detector on the ground because it gets scattered by the atmosphere.
Right.
And you can see that effect easily when you look at the sun, like during a time when there's a lot of smoke in the air from forest fires. Even at noon, the sun could look really red, like blood red in color. So what's happening there? Well, the smoke particles are larger on average than the particles that make up the atmosphere on the day when the sky is nice and blue. And so not only are the shorter wavelengths scattered by the smoke particles, but even the longer wavelengths, so that only the very longest of the optical wavelengths, like the orange and the red, actually make it to your eyes. The rest of it has been scattered around the air.
Mm-hmm.
So, and with this sort of analogy here, these reflection nebulae are blue because the blue light scattered more than the other long wavelengths. But the point is that when we look at open clusters like this, that we say that they're young, order of 100 million years in the case of the Pleiades, one naturally would think that when you saw the first image showing you the reflection nebula, so you need a telescope to see it, you can't see with your eyes.
Right.
It's not sensitive enough. That you think this is the leftover interstellar matter from the formation of the open clusters. In fact, we would expect that.
It was my first thought the first time I saw it.
Yeah, and many people thought that was the case. And in fact, it's analogy for that, if you want to think of analogy again, is I show up, Robert, at your house, uninvited, and you let me in, and I say, oh, Robert, you must be baking stuff today. And you're like, well, how do you know that? Well, I see flour on your countertop. I see, salt laying there, and some of your dirty bowls are in the sink.
Right.
And so I see the ingredients that you use to make the object that you are making, a cake or cupcakes or cookies or whatever it is that you're making. So I see the leftover debris, if you like, from the formation of the things that you want to eat.
Right.
Same as this case. So that status was sort of settled for many, many years.
Is that this was the leftover gas and dust?
That's right, from the formation of the Pleiades. Until somebody did something smart.
They measured the motion of the stars?
No, they measured the composition of the interstellar matter.
The dust and everything.
Yeah, they measured its composition, and then they compared it to the composition of the stars. And they don't match. It would be like you thinking, and I'm not saying this is true, but we're use a thought experiment, that a certain individual is your father. And you thought this all your life till the age you are now. And then for sake of fun, you go on one of these DNA sites,
right,
and you compare your DNA to your father and find out they don't match. You are not the biological son of your father. Your composition, in other words, your DNA is different.
Right.
And that's what happened in this case. So the story is, this is not the leftover material that we're seeing here as a reflection nebula from the formation of the Pleiades. What it is an ordinary, independent sort of cloud of interstellar gas minding its own business in orbit around the Milky Way. And it just so happens that the Pleiades star cluster is moving through that gas at this moment in time, lighting it up to let us see it as this reflection nebula.
Yep.
So they are independent of each other.
Kind of neat.
Kind of neat for sure. Now, if you wonder where are the Pleiades, right? Where are these stars that make up the Pleiades, the heart of it? How would you find that? Robert, do you want to explain what we're seeing here?
Okay, well, almost everybody can find the constellation Orion because of the three belt stars.
Why did they give it? Why is it 3 stars in that belt?
I don't know.
That's the rank they gave it, remember?
Oh, yeah, three stars?
They only gave it 3
They
stars.
only gave it 3 stars.
Somebody didn't like the constellation.
Yeah, only an ordinary belt, not a great one. But anyway, so you've got Orion's belt stars. So you can follow that line up to a bright red star called Aldebaran, and that is the eye of the bull. It is the eye of Taurus, the constellation Taurus. And it is one of the few stars that's bright enough that you can actually see the red color. Usually, most of us can. And if you can find Aldebaran, kind of like what we're showing you here on this picture, the Pleiades is essentially right above it. And like Wayne said, almost everybody can see it, if nothing else, but as this smudgy patch there above Aldebaran.
Now, if you had binoculars, even a small set of binoculars,
you see dozens of stars.
Yeah, look at the Pleiades. Take the time and effort to go out and have a look. You'd be really amazed at what you can see. And through a telescope, sometimes it's disappointing because if your telescope, depending on the eyepiece you use, you can zoom in so much, you only see such a small fraction. You don't appreciate the size of it. Mm-hmm. So when I look at the Pleiades through my telescope, I like to use an eyepiece that has a very low magnification because then I can see a wider area and I can capture more of the stars in a single view through the eyepiece.
Right.
So, yeah, so it's kind of cool in that sense. But that's how you find it, in case you're wondering. Now, what is this paper all about? What's the big deal? So, Robert, your turn.
Woohoo! This picture shows the full extent of the Pleiades cluster. All the stars that have a similar composition, moving in the same general direction, the same general way, but this shows the extent of that cluster, how far the stars have been pulled apart by their passage through the Milky Way and near other stars and near each other and been thrown out and pushed into different directions. And this is what happens to open clusters. They're in the galaxy, so relatively speaking, they're in close to a bunch of other stars. So slowly but surely, they're pulled apart.
So they're dissolving or
They're
evaporating.
dissolving or evaporating into the Milky Way at large.
Right.
And the Pleiades has been demonstrating this because it has been pulled apart. That green dot in about the center, you can see Orion, you can see Taurus above it, and that green dot is the Pleiades you can see. There's also the Big Dipper up there. It does basically 0 degrees up there towards the north at the top of the picture. So this gives you an even clearer view of how to find the Pleiades. But it also shows what this paper was trying to say. This is a huge complex. This takes up a very large portion of the sky.
So what we see as the Pleiades that we showed in the previous two slides back, that is only the core of a huge structure that's spread over a large area on the sky.
Right.
That's what we're seeing.
Pretty much.
It's the peak of the mountain. Right? You're at the peak, but you don't appreciate what is the actual size of the mountain itself.
Until you back up a little bit. Yeah.
Yeah, to get the full view of it. So, and all of this comes from the very, if you like, very accurate measurements that we get both from the test spacecraft and Gaia.
Right.
It just shows you what type of things you can uncover when you have really precise measurements of different properties. And that, in some sense, is the motivation to even improve future generation of spacecraft.
Right.
So you never know what they're going to unravel in terms of the mysteries.
This gets into a question I was asked at my talk I gave last night, which was, where are the companions for the sun? The sun may not have been made in a binary, but it was almost certainly made in a cluster like this.
Or yeah, it's sometimes we call it like an OB association.
Right. And so where are its sibling stars? And the answer is spread out through the Milky Way because of the processes that's tearing apart the Pleiades.
Yeah, so imagine you have the sun and let's make up a number, 5 other siblings that have formed nearby. And over time, those other siblings that are on slightly different orbits around the Milky Way than the sun, they get spread out.
Right.
And so what happens is, after 4.5 billion years that the sun's been here,
You're nowhere near your siblings.
no, we've gone around the Milky Way about 18 times in those 4.5 billion years. So your brother and sister can be on the other side of the Milky Way from our vantage point.
Right.
But to figure out what is a sibling, what would we measure in other stars? What
We would
look for?
measure their composition.
In other words, their DNA.
Yep.
To see if they're related. Just like you know, if you have a brother, how do you know for sure it's your brother? Well, DNA
and every
matching.
now and then there is a paper that pops up that says, hey, we found one. And then other people look at it and go, well, no, not quite.
Yeah,
so far.
So we've been looking.
We've been looking.
And we've looked at a lot of stars. So wherever our brothers and sisters are, they're not nearby. We would have found them by now.
Yep.
So, yeah, who knows? And of course, you can't rule out the possibility that the sun did form as an isolated star.
You can't rule that out, but it's so unlikely.
Most stars formed inside giant molecular clouds, and then where those regions of formation, they contain anywhere tens to hundreds to even thousands
of stars.
In globular cluster cases, millions of stars. Yep. So chances are probably not going to be a single.
Yep.
Okay. Now bringing it a little closer to home.
Just a little bit.
A little bit. Interesting paper that just came out recently. And it involves Mars, and it involves the fact that for the first time, they've actually detected static electricity on Mars.
Oh, okay.
Now, if you think about the moon, remember there's levitation of the dust due to the electrostatic. It's not so surprising then that you're going to find it on Mars.
Because there is some atmosphere, even if
There's
it's
some
very
atmosphere,
rarefied.
and you got dust, and it's very dry.
Yeah.
And so when things move around, you have friction. So the best way to understand it is you could do this experiment. I don't know if you've ever done this before, but try this. Take a comb, plastic comb, run it through your hair if you have any.
Right.
And if not, go to somebody else who has hair. Run it through their hair with permission.
Oh, no, do it by surprise.
Yeah. You don't want to start a fight here. Now.
Okay.
So run the comb through somebody's hair, put it that way, and go a few times. Let's say 10, 20 times, just so you know you got it right. And then go to a tap, a faucet, and turn on the stream of water very slightly. So it's not a dripping, but it's a steady run, but the stream is very tiny.
Right.
Okay. Now take your plastic comb and go up close to the stream of water, but not right touching it. And you actually can bend the change the direction of the stream of water.
Right.
Now, why does that occur, Robert?
Well, because water is a polar molecule. It has a dipole moment, a magnetic field. And so electric fields and magnetic fields are really just different ways of looking at the same overall field. And so that water gets pushed away or pulled towards the comb, depending on which type of charge the comb picked up.
Yeah. So the other thing you can do is you can take the same comb and you rub it, and you can pick up like pieces of paper. You ever get a package from, I don't know, you don't want to mention a company, but some company that you ordered and arrives, right? And you open up the package, they open up the box, grab it before the porch pirates get it. You know, that's always the secret. You start opening it up, and you get some of this plastic wrapping that contains the item you had ordered, let's say. And then you look, and you got this little piece of clear plastic on the end of your fingertips, and you shake it, and it just
won't go
away. How do you? And every time you try to pull it up, that sucker jumps to the other part of your hand.
Right.
Right. And it's difficult to get. So what causes that, Robert?
It's the same thing. It's static electricity and the attraction to the hairs, the tiny microscopic hairs that are on your fingers and things like that, and they pick up charge because they're rubbing against things, and
Now, this time of the year, it's winter here.
It's really worse.
It's winter here, so it's extremely dry.
Yep.
So you rub your feet along the top of the carpet, and then touch the doorknob. What's going to happen? Or touch somebody else? Zap. What does that do to? Why does that occur?
Well, because you've built up a nice charge around you by rubbing your feet against the floor. And if it's got a high enough voltage, it can cross the air gap.
So the act of rubbing or friction, if you want to think of it that way, right, kinetic friction, then can cause charges to be separated.
Right.
So the object's no longer neutral, meaning an equal balance of negative and positive charge. So if you can do a charge separation, and then when that charge wants to come together in a different situation, that's when you get that flow of electrons. So that's your static zap.
It wants to equalize.
It wants to equalize. And that's what we have essentially what's going on Mars. That's what this Nature paper is all about. And
go ahead.
I was just going to say, in this case, it's the same kind of thing. It's moving objects rubbing up against each other, but a lot of it involves dust. And one of the things Mars is notorious for are these giant dust storms that happen occasionally. And with the movement of fronts, atmospheric fronts, weather fronts on the surface, you can get the dust moving across the surface, and you can build up electrostatic charge. And the other thing we have that's moving around in terms of the air on Mars are these dust devils.
Right.
And we've talked about them in the past, but we've observed hundreds and hundreds and hundreds and hundreds, probably thousands of these dust devils so far over the time that we've landed, rovers and landers on the surface of Mars. And so with that motion again of the dust and what air is on Mars, it's not surprising in hindsight, right, that you would have a situation where you have essentially lightning on Mars.
What's surprising to me is that they haven't discovered lightning. I thought they had.
They have. They recently discovered that.
Wow. Okay.
In fact, the Perseverance rover has heard. I mean, and this is part of this paper too. You hear it on the microphone that it carried. The static discharge, the discharge of the lightning, the zap, both related to the dust devils and these fronts. So they've seen images of lightning on Mars and also heard the thunder, if you like, the effect, the noise that it generated, right?
Interesting.
Yeah, and so Mars's atmosphere is such that you can still pick up some of that noise,
right?
Some of the effect of it. And that's essentially what this is all about. In fact, if you go to the slide, you'll see sort of a graphic that illustrates that. So you see the rover there on the cartoon illustration. Notice that it's a ground discharge that can happen from the rover itself to the ground. And you can see the discharges happening inside the dust cloud as that stuff is moving around. And you have charge separation. And, of course, you want to equalize is where you're going to get the discharge. Just like, clouds in the ground in terms of lightning here on Earth. Or cloud to cloud, you get the separation of that charge.
As we've now found out, with sprites and trolls and so forth, you can get it cloud to ionosphere.
Yes, exactly. Anyway, you think you can make basically a circuit, a wire, in some sense, to allow a path of flow of the charge itself to equalize.
Right.
You're going to have that in any type of environment. I can think of a planetary environment in which you figure this is going on all the time. You know what I'm thinking of? The planet.
Jupiter?
No, well, that, but a planet that we may step on maybe someday if we have the right technology.
Um,
Twin to the Earth?
Venus?
Venus.
I would never think of trying to step on Venus, but that's me.
You got to have the technology. You got to
Yeah.
have the pressure suit that can
The
survive.
pressure suit that will survive the temperatures and the pressure and the acid atmosphere.
Someday,
okay.
a human being will walk on the surface of Venus.
Yeah.
Anyways, so
I can believe it. We're pretty clever critters. We'll figure something out.
oh, definitely. Give enough time and enough
And enough
engineering that
resources.
gets done, we'll do that. So yeah, so it's not that unusual. We see electricity, and you mentioned Jupiter. We see it all over the place in lots of different environments, and so having it happen on Mars shouldn't be that big of a discovery, but it is, and people have now will study that in more detail.
Yep.
So it's quite interesting when you think about it. Now, going from the really close back to the really far again,
Really far.
really, really, really far. There's a study done on looking at jets coming from quasars. So this was data that was taken. I'll show you the slide in a second here, but right now, this is the title page, if you like, of the paper itself, taken with the giant meter wave radio telescope. So this is a huge thing. I mean, this telescope is like what 50 or so meters across,
Something
or
like
something
that.
to that effect. So it's a giant structure, the giant meter wave radio telescope, the GMRT. You know, I had time on this before.
No, I didn't.
Yeah, so back when I was a postdoc, this would have been back when I was in Illinois. So this would have been like 2005-ish, something around there. We were looking at this relatively unusual galaxy cluster, Abell 447.
Okay.
And it contains a really massive black hole in its center. And there's some other weirdness going on with the cluster that I don't have time to really go into. And one of the things we wanted to do was get some good observations at radio, looking to see if there's a presence of any jets or this kind of stuff. And part of the people that were collaborating on the project had access to the telescope, which is in India, and they put in a proposal of all of us to get time. And we actually got time on the telescope and
Cool.
got data.
Excellent.
And we could measure the radio power, or at least upper limits to it, that's being produced by the active galactic nuclei that's at the center of the biggest galaxy in the cluster itself, which is kind of cool when you think about it.
Absolutely.
So, and this particular study then was looking at jets. So these are from active galaxies. Now, an active galaxy is one in which you have a supermassive black hole at its very heart, as center. And outside of the black hole proper, outside of what we call the event horizon, we would have an accretion disk of material, gas and dust was spiraling around. Think of water going down your bathtub when you pull
Except
the
this
plug.
water gets hotter and hotter and hotter.
Yeah, in fact, it gets so hot it can reach millions of degrees, and at that high temperature, it can emit lots of X-rays, as well as other wavelengths of photons, of course. And what happens is the magnetic field associated with the material itself gets all twisted up, and it forms most cases, is not all cases, but a lot of cases, this collimated beam. And that collimated beam consists of magnetic field and charged particles, and these charged particles get trapped or entrained by the magnetic field, and they spiral around the magnetic field lines. And in doing so, they emit light. That's fundamental theory of Maxwell's equations. An accelerating charged particle will emit light.
Electromagnetic radiation.
photons.
Light.
Yeah, in this case, it's predominantly a radio wavelength, so synchrotron emission is what the process is all about. And you get these long jets that come out, one on sort of, if you want to call it, north of the accretion disk, above it, and one below it, but outside of the black hole. They're not coming from inside the black hole.
Right.
They're coming from outside the black hole. Now, the details of how all this works is something they're still working on. It's not completely solved. How do you make the jet originally? How does the jet get launched? How do you maintain the jet? All these kind of things. Very detailed magnetohydrodynamics calculations, as we say, interplay of matter, charged matter, and magnetic fields and electricity. All these things are all important that you have to consider. And what we know is that at least for the giant radio galaxies and also for the quasars, that occasionally you'll have these beautiful radio jets that come out. Now, this particular study actually discovered that some of these radio jets, and you see that on the image. Now, this is not an image taken with the radio telescope. It's data taken by the telescope that's made into these spatial images,
Right.
right? So a representation of the data itself. And what they discovered was a set of 53 of these supermassive black holes, these active galaxies, these radio galaxies that have these jets. And you can see there on the far left, there's a blob that sort of goes to the, if you like, the upper left, and a blob that shoots down to the lower right. These are the radio lobes. So this is what you're detecting then at radio wavelengths. And in the center then, sort of the narrow part, that would be where the giant supermassive black hole is located. Now, we've seen them before. There's no mystery. These things have been observed since radio telescopes were invented.
In fact, I can think of one nearby galaxy that has an optical jet.
M87, yeah, in the Virgo cluster. And so, in particular, these radio active galaxies, these radio galaxies, these jets are, a certain length. But what they're finding in this study is that some of them, right, have lengths, jet lengths from one end to the other, that's over 7 million light years in extent.
That's big.
And that would put them at about 50 times the diameter of our Milky Way galaxy.
Right.
So and the interesting thing that I find is not that they're so long, it's that what is the exact physics behind how they can maintain their structure for such a long distance.
Right.
That's the interesting part. How can they stay collimated like that or maintain their, their physical shape for such a huge distance?
Because as rarefied as it is, there's still stuff there, plus itself putting up resistance to the motion. So how does it maintain itself for that kind of distance?
Now, it's interesting, sort of a little backstory on these radio galaxies I like to say about is when they were first discovered in the radio, you see this sort of these radio lobes, and then people would have to go to an optical telescope to look to see what's there, and they find usually this elliptical-like galaxy sitting, at the center of these radio lobes, and eventually figured it out that the only thing that could really power them are these supermassive black holes. And we have one in our galaxy. It's not an active galaxy because we don't have that big accretion disk, but the one that's in our galaxy, which we took the image of the shadow of it with the Event Horizon telescope, it has a mass about 4 million times the mass of our sun. The optical jet you mentioned, the M87, that's billions of times the mass of our sun. So typically, these supermassive black holes are just that, billions of times the mass of our sun. So they are monsters, right? They are huge in that sense. Okay. So initially when they were discovered, people were thinking, maybe we can use them to measure distance. And I mean distances over large distant range of our universe, cosmological distances.
Right.
And you might wonder, how the heck could you do that? Well, you could do it if these things were a standard yardstick.
In other words, if they had a known standard length.
Yes. If the distance from, let's say, the upper left, if you look at the far one on the left, all the way to the lower right, if that in terms of physical units, kilometers or meters, whatever you want to use, if that was roughly the same from one radio galaxy to another, then we could use it to measure distance, because the further away it would be from us, the size clearly would get smaller, and the smaller its apparent size. And if you double the distance to something, its apparent size is half. Okay? So then we could use that information to actually measure the distance to these individual objects.
Right.
Now, it turned out when they did follow-up study on that idea that the actual length from one side of the jet to the other, it varies by a lot from one radio galaxy to another. In fact, it varies so much. There are other techniques that we use that get a much more precise measurement of distance than using these radio galaxies. But these radio galaxies, and this was in the 1950s, these radio galaxies caught people's attention. Right. And when people did do follow-up work using optical telescopes, they actually discovered things like these quasars that we know and love today.
Quasi-stellar objects.
Yeah. So it's quite interesting, the whole history behind all of that stuff. And by the way, the radio telescope that was used for this study is the one you see on the right. That's the giant meter wave radio telescope in India.
Okay.
Interesting stuff.
Yes.
Now, Robert,
Yep.
if you know of somebody who would like to get into the STEM field, to
Yeah.
learn about these type of objects, or maybe build the equipment because they want to get involved in engineering, or maybe they want to get in the arts and become journalists and describe what we're doing as scientists
Accurately report it.
and accurately report it, and get away from the fact that they think 3i Atlas is a UFO. Never write that down in a story because you will not be rich and famous. You will
Right.
get a reputation you don't want to have. Dig, dig, dig. Now, if you want to do all those things and plus more, what do you do, Robert?
You
What
go
do
to
you
higher
do?
education. You educate yourself.
And what's the best place for higher education in the whole known universe?
Well, I guess University of North Dakota. It's
University of
definitely a
North-
good place.
It is, for sure. So come here, come on campus, go online. You could be on the moon, right? And if you are, send us an invitation. We'd like to visit you.
Yep.
You can take courses anywhere you want in the world if you don't want to come here to North Dakota. I don't know why you wouldn't want to come here. We have great hockey and other stuff that goes on.
Yeah.
And the summers
it's-
are fantastic.
It's not like it snows all the time.
Just for a couple months and that's it. You get used to that.
Yeah.
It's just a distraction, right? You don't want to be out. Imagine if you lived in Hawaii, Robert. How much work would you get done? You'd be out surfing every day and
I don't
enjoying
know
it,
about surfing, but yeah, I'd be enjoying the sun. And
drinking pina coladas
Yeah.
underneath a palm tree.
Yep.
All that kind. So it's too much distraction. You want to live in a place like North Dakota.
Yeah.
It's perfect for doing your research and your studies.
Yeah.
So
Okay.
come here. We have, anyways, if you do come here, come visit Robert and I. We love to see you.
Absolutely.
Now,
really
Robert, our next podcast, we're getting close to Christmas, so
Yep.
the next one will be on December the 9th, week from today. And then we'll do another one after that, which is December 16th.
Right.
And then that's it, because you're adios, amigos.
Because the 23rd, when the next one would be, is when I'm heading to visit family and everything.
And remember, as I said before, always deposit your Christmas gift to be before you leave.
Before I leave.
That way you don't have to worry about someone breaking in your place when you're gone and stealing my gift.
You got
Because
it.
I know it's so valuable. Somebody, if they knew it was there, you'd have lots of people trying to get through.
Trying to break through the
Trying to get through
security.
your window or something. Now, the other thing is we also leave you with a quote
Okay.
at the end of our podcast. So today's quote is by Chandrasekhar,
Subramaniam Chandrasekhar.
very famous person who did a lot of work related to stellar remnants like white dwarfs and
Like
so
white
on. In
dwarfs.
fact, he won the Nobel Prize in Physics for that.
Mm-hmm.
And here's what Chandrasekhar said of black holes. How
Okay.
fittingly. The black holes of nature are the most perfect macroscopic objects there are in the universe. The only elements in their construction are our concepts of space and time.
Ooh.
Deep.
Interesting. Yeah.
Anyways, if you like this podcast, please don't forget to give us a big thumbs up. Subscribe if you haven't subscribed. Tell any friends that you may have that
Yep.
we exist, and we'd love to have you for
Have
company.
you looking in? Yeah.
Have you looking in and view our podcast anytime you like, and view it more than once. If you
Yeah.
kind of missed what we said a little bit, there's no harm in going through it again and again
And again.
and again and again.
Our show up live and let's chat.
Anyways, thank you very much for watching, and we'll see you next time.
Bye, folks.